Let us begin. And like I told you, in the last lecture, we had discussed about this various representation of complex numbers. And now I am going to talk about this something called extended complex plane. So extended complex plane and stereographic projection.
So please share your screen.
Yeah, yes, just a moment. Let me just write the title. Projection. Yeah, thank you. So I forgot to join even from my iPad, it seems. Okay, thank you for reminding. Okay, it seems to be working. Let me see. Yeah, so are you able to see my screen?
Yes,
Yes.
sir, we can say.
Yes, sir. Yes, sir.
Fine. So therefore, yeah, that's good. So let me now. Yeah. Okay. So we are going to study extended complex plane and stereographic projection. Okay. So whatever that means. So just hold on for a second. There is another somebody has started another meeting. Let me just tell them that that's not the correct meeting, and I'll come back. Just hold on for a second. Yeah. Okay, I'm back. So you can see the screen, right? Yes. Okay, so as I said, I want to discuss now about extended complex plane and stereographic projection. So I had already told you in the last class briefly what we are going to have. So we are going to identify the set of complex plane as with points in a punctured sphere. And since in the sphere we are going to have one more extra point, so the sphere can be seen as kind of one point compactification of the complex plane. So anyway, those of you who do not know this, because your topology course is only going to you will have the topology course this semester, so we can forget this for the moment. But let us see how we can associate the set of complex numbers with the points on a sphere, okay, except for one point. Okay, so here the important thing that I need to have is a picture. So let me draw the picture first carefully. So this is my coordinate system. And now I need to have circle. So I want to use a different color. Maybe I use this one. And I select this one. Okay, fine. Whatever color it is coming, okay, so now I have to draw a sphere on this. So this is the point 0, 0, half. I am going to draw a sphere centered at this point. So let me have a circle first. Okay, and yeah, so this is sphere centered at 0, 0, half. Anyway, okay, so the picture is not very accurate, but anyway, you understand what it is. So it's a sphere centered at 0, 0, half, and this point is 0, 0, 1. Okay, so and this is my origin, which is 0, 0, 0. Okay, and now the point is that I want to identify complex points on the complex plane with points on this sphere. Okay, except for the one which is in the north pole. Okay, so that one means that is the point 001, that is not going to be identified with any of the points in C, but I am going to identify rest all other points with points in the set of complex numbers. Okay, so how do I do that? Okay, now so what I'm going to do is that we are going to, let's say, start. So I'll write down everything explicitly. So what we are going to do is that we are going to start by taking a point on this sphere. So let's say this point, so call this one UVW. This is a point on the sphere, and then I am going to find out a complex number, or rather a, a tuple or a pair of real numbers in the complex plane or in R2. Okay, so how do I do that? What I am going to do is that I am going to extend the, or I am going to draw the straight line passing through the North Pole and the point that I have taken. And now you can imagine that if you, for example, if you have a sphere, and like let's say you have a table and you have a sphere that on the table, and then if you take any point on the sphere and try imagining that joining that point with the North Pole, then you will see that you are going to hit the table, right? So similarly here, what happens when I try to join 001 and the point UVW? So I'm going to hit somewhere here in the complex plane. So which, let's say, the point it looks like A comma B comma Z. Okay. So the points of this form UVW in the sphere, I'm going to identify them with this point A comma B comma 0. Okay, so that is what we are going to do, and what we are going to see. Of course, I have to write down for you what are the formulas of A and B. Means given UVW, what are the points of A and B, and if there is a prescription to start with a point on the complex plane and get back a point on the sphere, so that that point in the sphere gets mapped to that particular complex number. Okay, so I have to give you a two-way prescription so that you can identify every point on the sphere except for the North Pole 001 with every other point in the plane R2. Okay, or in the complex plane. So is the picture clear what I'm going to do? Yes.
Yes, sir.
So I'm going to,
Yes, sir.
by taking any arbitrary point on the sphere, and I'm going to means in your, you can imagine itself that I'm going to draw the straight line passing through the North Pole and this UVW, and that's going to hit somewhere in the complex plane. So means, or rather the Z equal to 0 plane, because here the picture is 3D picture. So I'm going to get a point A comma B comma 0. Okay, so let us see how does the means formula look like, and how do I if I can give a two-way prescription to get this correspondence. Okay, so to start with, so let me first denote this sphere by S. So yeah, so I have the sphere S. So the sphere S is the set of all points U, V, W on R3, let's say, such that, so U cube plus, sorry, U square plus V square plus W minus 1 over 2 square. So this is equal to 1 over 4. Okay. So I have drawn, as you can see, my center of the sphere is 0, 0, half, and I have drawn a sphere of radius half. Okay, from centered at 0, 0, half. So that is the sphere that I have drawn. Okay, now this sphere is clearly, as you can see, is lying on the means xy plane. Means like, it means when you look at it, it touches the xy plane at the point 0, 0, 0. Okay, so for example, if I put u equal to v equal to 0, you see that that satisfies this equation of the sphere. So that point lies on the sphere, as well as it's lying on the xy plane. Okay, so or the z equal to 0 plane. Fine. So this is what is the sphere. And now let us try to give the prescription. So to every point UVW on S not equal to, I should write, not equal to 0, 0, 1. So I am going to avoid this point. We associate a point A comma B comma 0 on R3. Okay, so this is what I am going to associate. And how do I get this? By joining the line passing through UVW and 0, 0, 1. Okay, so I'm going to do this. Okay, so I have said that when I extend this line joining 0, 0, 1 and UVW, it cuts like it hits the xy plane at the point AB0. So therefore, what do I have? I have the collinearity of these 3 points. Okay, so from the collinearity of UVW 0, 0, 1 and AB0, what do I get? I am getting the following. So this we get. So if you write down the expression for collinearity, you will get U minus 0 divided by A minus 0 is equal to V minus 0 divided by V minus 0 and equal to W minus 1 divided by 0 minus 1. Okay, so that's what is the collinearity going to give you, and therefore from this, hence what I get is that A is equal to U by W minus 1 and B is equal to V by W minus 1, right? So therefore I am going to associate a point UVW on S to the point A comma B on R2 or A plus IB on C, such that A is equal to U divided by sorry,
Sir, it should be 1 minus W.
thank you, 1 minus W, because this ratio is actually 1 minus W. Thank you. So 1 minus W. Yeah. So A equal to U divided by 1 minus W and B equal to V divided by 1 minus W. Okay. So this is the association that we are going to have. Fine. So is it clear? So if I start with this point UVW and try to draw the line joining 0, 0, 1 and UVW, it's going to cut the xy plane at the point U divided by 1 minus W, comma V divided by 1 minus W, comma 0. Fine? Clear?
Yes, sir.
Yes, sir.
Now we
Yes, sir.
now if we like in the sense if we associate UVW to U comma 1 minus W, V comma 1 minus W, we can show that it is a bijective correspondence or bijective association, or it's a bijective map. That's it. Okay, so this association is bijective. So how do I see that this association is bijective? So that means what I am saying is that whenever if I start with two different points on the sphere, I'm going to get two different complex numbers or two different pair of real numbers. And if I am given a pair of real number, I will always be able to find one point on the sphere which is means which will correspond to this particular point. Okay, so I am going to I have to prove these two things. Okay, so let's first take care of the surjectivity. Okay, so let us first see that this is surjective. Okay, so here I am going to start with a point a comma b comma 0 or a comma b. So let a comma b is in R2 rather. So what do I have to do here? I have to give you the recipe to find out UVW in the sphere, so that when you take these UVWs, you should get back that U divided by 1 minus W should be equal to A, and V divided by 1 minus W should be equal to B. Okay, so here I am just going to give you the coordinates explicitly, and I will ask you to check it yourself. Okay, so take U equal to, for example, A divided by A square plus B square plus 1. Similarly, V you can take B divided by A square plus B square plus 1, and you can take W to be A square plus B square divided by A square plus B square plus 1. So you can first of all check that this UVW, the way I have defined this UVW, this if I take the triple UVW, that is going to be a point on the sphere, number one. And finally you can check that U divided by 1 minus W is going to be equal to A, and V divided by 1 minus W is going to be equal to B. Okay, so that will give you that this association is definitely surjective. So that means no matter what complex number you start with, you will always be able to get 1 point in the sphere. Okay, so that is what it is. And next is the part which I have to prove is the injectivity. Okay, so injective. So that means I have to show that if I take two different points, I am going to get two different images. Okay, so I have to do that. Okay, so let us do that. And so let us start with 2 points which might have the same image. Okay, so let u1 v1 w1 and u2 v2 w2 belongs to s minus 0 0 1. So anyway, I am always removing this point. So let these are the 2 points such that they correspond to the same complex number. So therefore what condition do I get over here? If they correspond to the same complex number, tell
It
me
is
what.
they are same. The
So
points are same, equal.
no,
Component wise terms are same.
I have to prove that, but I am saying that at this moment, all I means I am starting to prove injectivity, and I am saying that let us take 2 points which are going to the same point. Okay, then we will show eventually u1 equal to u2, v1 equal to v2, w1 equal to w2. Okay, so that is what is our goal. Now I am saying that we have started with 2 points, and let's say their images are the same. So what does it mean? So what do we get?
U1 U1 by
U1
1 minus W1 equals to U2 by 1 minus W2.
Similarly, v1
V1 by 1 minus W1 equals to.
v2 by 1 minus w2. Very good. So this is what we get. Okay, that's great. Now if you see, if I equate these two, I'm going to get u1 upon u2 is equal to v1 upon v2 is going to be equal to 1 minus w1 upon 1 minus w2. Correct? Yes. So all these ratios are the same. That is what we are getting. So this implies that. So let us call it alpha. So equal to or lambda c. So let us call it lambda. So this all these ratios are same. So let us call the ratio to be lambda. So what do I have? I have u1 equal to lambda u2, v1 equal to lambda v2, and I have 1 minus w1 is equal to lambda times 1 minus w2. Okay, great. So I have this, and therefore, what can I say here? I get that half. So yeah. So in other words, of course, I can, if I subtract half from both sides, what I will get. Anyway, we will see what it is. How I am going to use that. Anyway, so this is what I get. Okay. Now the point is, I have u1, v1, w1. lying in the set S. Okay, so note U1, V1, W1, this point lies in the set S. So that implies what? That implies U1 square plus V1 square plus W1 minus half square is equal to 1 over 4. Okay, this is what I have. So once I have that, I know what is U1 is. U1 is lambda U2. So I can put lambda square U2 square plus lambda square V2 square plus here I need to have omega 1 or sorry W1 minus half, but I have 1 minus W1. So if I subtract half from both sides, what am I going to get? I am going to take a square. So what am I going to have? I am going to have lambda minus lambda W2 minus half whole square is equal to 1 over 4. Do you all agree to this?
Yes, sir.
Okay, great. So I have this. Now let us try to take this lambda out of the picture. So let's take it common. So that implies if I take lambda square common, I get u square plus u2 square plus v2 square plus 1 minus I think w2 and minus 1 by 2 lambda whole square is equal to 1 over 4. Fine, great. And if I now open up this whole thing, what am I going to get? Let us see. So this is lambda square, and then let me just see what do I get over here. I can, if you notice carefully, I can write this one as, how can I write? So I'm going to write it as u2 square plus v2 square plus uh, w2 minus half square plus, and then I have to w2 minus half square, I have to add and subtract. You see this is minus, and plus I have 1 minus w2 minus 1 over 2 lambda whole square is equal to 1 over 4. I hope I have done it correctly, but yeah, I have to see that. Okay, so anyway, I have this, let it be. Now this one implies lambda square. So what is this quantity? This quantity is equal
1
to
by 4.
1 by 4.
By 4.
Absolutely, because u2, v2 and w2 is on the sphere, plus minus w2 minus 1 over 2 square plus 1 minus w2 minus 1 over 2 lambda whole square is equal to 1 over 4. This is what I have. Okay, great. So now can I see what do I get? Let me try to simplify this. Lambda square, I have 1 over 4 minus omega 2 square. Should I write it explicitly? Okay, let me write it. Omega 2 square minus omega 2 plus 1 over 4. And here what do I get? Here, how should I write this? Let me see, this is plus 1. If I, yeah, let me completely open it up and then write it. So what am I going to get? I am going to get 1 minus 2 omega 2 plus omega 2 square, and then minus 2 times, so that's minus 1 minus omega 2 times 1 over lambda plus 1 over 4 lambda square. Okay, I hope I have done things correctly. I do not know. So here certain things are going to get cancelled. What are going to get cancelled? This 1 by 4 I can get rid of with this 1 by 4. I have a minus w2 square which I can cancel here, and then eventually what do I have? Eventually I have lambda square, and I have minus w2, so 1 minus w2, so here minus 2w and plus minus 2w2 and 1 plus 2w2, so 1 minus w2, and then I have minus 1 minus W2 into 1 over lambda plus 1 over 4 lambda square. This is what I have is equal to 1 over 4, and if I multiply by lambda, again this part is going to get cancelled with this thing. So eventually what do I have? I have lambda square minus omega 2 lambda square minus 1 minus omega 2 lambda is equal to 0. Fine, so here I can take lambda square common, so 1 minus omega 2 minus 1 minus omega 2 times lambda is equal to 0. That gives me lambda into 1 minus omega 2 into 1 minus lambda is equal to 0. Fine, agreed? Or maybe lambda minus 1. Sorry, not 1 minus lambda, but lambda minus 1. Doesn't really matter. Okay, so we are going to get this. Fine. I hope I have done the calculations correctly. Yeah. Okay, now let us try to see what am I going to get. I have my this point u2 w u2 v2 w2 is not on is not the north pole, that is not equal to 0 0 1. So therefore in particular w2 cannot be equal to 1, right? Do you all agree to this?
Yes, sir.
If I
Yes, sir.
Yes, sir.
That's right.
on this sphere, if you take any point which is not the north pole, of course that cannot have the last coordinate to be equal to 1. So therefore we have, since w2 is not equal to 0, we have lambda equal to 0 or lambda equal to 1. Fine. Yes, that is what I am getting. Correct?
W2 is not equals to 1.
Sorry.
Not equals to 1. W2 is not equals to 1.
Yeah, I understand. Thank you. So since W2 is not equal to 1, I have lambda equal to 0 or lambda equal to 1. Correct? Great. Okay, so now let us see if I can have lambda equal to 0. So can we have lambda equal to 0? So that's the question. So now if I have lambda equal to 0, so that means what? Let us see. From here, if I have lambda equal to 0, so if lambda is equal to 0, this quantity is equal to 0, the numerator is anyway something which is non-zero over here. So what do I get? I am getting 1 minus w1 must be equal to 0. Clear? If lambda is equal to 0, then I get 1 minus w1 must be equal to 0. Clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, now can we have this? So lambda equal to 0 implies 1 minus w1 is equal to 0, which implies w1 is equal to 1. But again, that is not possible, correct? Again, this is not possible, not possible. So we have lambda not equal to 0. Now in this factor, I see lambda cannot be equal to 0, w2 cannot be equal to 1. So I can cancel these two things. What am I left with? So we have, tell me what am I left with?
Lambda equal to 1.
Yeah, very good. Now if lambda is equal to 1, what can I say about u1, u2, v1, v2 and w1, w2?
U1 equal to V2.
Same.
Equal.
Equal.
V1
They are
Equal.
equal.
Exactly. So I get, hence I get u1, v1, w1 is equal to u2, v2, w2. Okay, so yes, it was slightly lengthy, but nothing complicated. So we got that, okay, it was just manipulating the equation, and eventually we got, if 2 points on the sphere, if they are mapped to the same point, those 2 points better be equal. So therefore our this correspondence that we have, that correspondence is a 1-1 correspondence. We have already seen surjectivity, so hence this is a bijective correspondence. Do we all agree to this? Yeah.
Yes.
Yes.
Yes, sir.
Fine. Great. So we agree to that. Now, okay. So here, let us try to observe few things. What is this special point 001? Okay. So I was telling you probably the other day that this is one point which will referred to as the point at infinity. Okay, so for example, in the real line, you say that you have two infinities, one is plus infinity, one is minus infinity. Similarly, in this case as well, you are going to have a concept of infinity in the set of complex numbers, and this concept of infinity here, you see, I can go towards infinity in several directions, right? In infinitely many ways I can go to infinity. So we are not going to have so many different notions of infinity. So here we are going to have only one infinity. Okay, so only one point at infinity that we are going to have. And I had told you in the last lecture that we are going to treat this point 0, 0, 1 as point at infinity. Okay, so that will be the thing now. So therefore, let us try to understand the dynamics of this point, like how does this point really behave, or how does the point near this point behave, and why do we call this point 0, 0, 1 to be point at infinity. Okay, is this clear what I'm going to do now? Fine, we are going to understand the behavior of this the points near 0, 0, 1, and thereby we will try to justify this nomenclature, what we said that this 0, 0, 1 should be taken as the point at infinity. Okay, fine. So let's try to do that. Okay, so we have the prescription already. If I have UVW, then you know it is getting associated to the point A comma B, where A is U divided by 1 minus W and B is V divided by 1 minus W. So okay, so this is done, hence this is so this is over here. Now UVW is connected to A and B. So where this we know A equal to U by 1 minus W, B equal to V by 1 minus W. Okay, so what is A square plus B square? So A square plus B square is therefore U plus V square divided by 1 minus W square, right? Fine. Now, what is U square plus V square in from the equation of the sphere? Okay, can we see that what is U square plus V square from the equation of the sphere? So equation of the sphere was U square plus V square plus W minus half square was equal to 1 over 4. So what is U square plus V square? So this is equal to nothing but
2 into 1 minus W.
W minus W square, so W into 1 minus W. Very good. So this is what I have. So what is A square plus B square? Let us substitute W divided by 1 minus W and 1 minus W square in the denominator. Now W is of course not equal to 1, so I can cancel one of them. So I get W divided by 1 minus W. Okay, good, fine. This is what A square plus B square is. Do we all agree to that? Okay, now let us observe the following. So what is so I am relating this point A plus UVW to the point A comma B, or in other words to the complex number A plus IB. Okay, so if I take the point A plus IB in the complex number, so let us call it Z. So what is mod of Z? Tell me what is mod
A
of Z?
square plus B square.
Square
A
root
square
A
plus
square
B
plus
square.
The square root.
The root is square.
Square root A square plus B square. Okay. Now imagine now if A square, or let's say if mod Z tends to infinity. So mod Z is a non-negative real number. So now if this is tending to infinity, then what can I say about the behavior of this from this equality? What can I say? The equality that I have just derived. If mod Z is going to infinity, then what can I say about, for example, the value of W?
W
W
tends to
tends
1.
to 1.
W tends to 1.
W tends to 1.
Very good. So then W
Equator.
tends to 1. Okay, that's good. First thing first. So W is tending to 1. Okay, now if W is tending to 1, then where does U square plus V square tend to?
infinity.
Zero.
Infinity.
0.
No, no, no.
0.
Be careful. What is U square plus V square? Just now you have calculated W into 1 minus W. And W is going to
0.
1. So therefore u square plus v square is going to 0.
Zero.
So u and v, these are real numbers. That is, individually, where are u and v going to?
Zero.
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 V square, both of them are real numbers, and their sum of the squares are going to 0. So individually they are also going to 0. So that is, u is going to 0, v is going to 0. Okay. So therefore, what do I see? If mod z is 10 to infinity plus infinity, then where does u v w as a whole triple, where do they go to?
Equator.
North Pole.
001.
Not 0, 0.
So if mod z tends to infinity, u v w tends to 0, 0, 1, right? So as we take complex numbers with higher and higher modulus, we will see that the points u, v, w, corresponding points u, v, w on the sphere, they are going to be closer and closer to the North Pole. Okay, 0, 0, 1. So therefore, now do you see why one would call this point 0, 0, 1 to be the point at infinity? Yes. So
Yes, sir.
the moment we take higher and higher values of
Yes,
mod,
sir.
we are on the sphere. If we look at the trajectory of those points, we will see that they are going towards 0, 0, 1, and that is the reason why this point 0, 0, 1 is called the point at infinity. Okay, so this is what it is, and in fact, I can even give you one exercise to do. This is even something more explicit. So, for example, let U to be this set U V W in S, such that W is some bigger than some W naught. Okay, so for some 0 less than W naught less than 1, so let's U to be this, and V subset of R2 to be the corresponding points on in R2 be the set of corresponding points, be the set of corresponding points in R2, then you can show that then V is nothing but V is the exterior of the circle centered at the origin with radius 1 upon square root of w naught divided by 1 minus w naught. Okay, so therefore what I am saying over here is that if I, let's say, if I try to draw the picture, let's have the coordinate system, and let us say if I, so what it says that if I am taking some neighborhood of this 0, 0, 1, so namely I am taking something where all these w's, value of these w's are bigger than some w naught between 0 and 1, so that means in the sphere I am looking at the points which are having certain height at least. So if I call w to be the height, if I am taking certain height in the sphere, then that those points are going to correspond to something which is exterior of a circle. So this is, these points are going to be those ones corresponding to the points. So where this is my square root of w naught divided by 1 minus w naught. Okay, so these, if once I draw this circle, I will see that this kind of the set u that I have written over here, that corresponds to the exterior of this circle. So you can see that the moment I increase the value of w naught and I go closer and closer to 1, so this radius is going to become larger and larger. So anything which is outside this circle is going to have larger and larger modulus, right? So therefore, like we are going closer and closer to 0 0 1 namely. Okay, fine. Is this clear? So this is something which you try to work it out, that you see that these points on U correspond to the V is going to be the exterior of this circle that I have drawn over here. So V is going to be that. Okay. So therefore, like that will even give you a better feeling about why, means how really we are going closer and closer to this point 0 0, means when we go closer and closer to this point 0 0 1, how the uh, absolute value is growing. Okay, so this is what is the exercise that tells us, and now we completely understand why this point 0 0 1 is called the point at infinity. Fine. Okay, great. So let's go ahead. So this was the brief description about the stereographic projection and the sphere, the stereographic projection and extended complex plane. So we have association, like for every number in the complex plane, we can associate one point on the sphere, and except for the point 0 0 1, if we remove that one, then we have a bijective correspondence, and the moment we like, and we can treat this point 0 0 1 as point at infinity. Okay, so this is what is the stereographic projection all about. Okay, so now we move on and we are going to study some topological properties of C. Okay, so I'm going to discuss some topological properties of C, and of course, since you are having the topology course now, you will see that some of the things that I say might not make sense at this moment. Okay, but they are going to eventually make sense. Okay, so if you do not understand something, you can of course ask me. I'm going to give all the definitions that are required, but anyway, you will see them more rigorously in the topology course. Okay, so as far as the topology of the complex numbers are concerned, that it's quite similar to that of the topology of the real numbers. Okay, so for example, on R we have a distance which was given by like mod of, for example, if I have 2 points x and y, the distance between these two is given by mod of x minus y. Okay, now similarly we have an absolute value on C, and this absolute value is going to define a metric on C. Okay, so we have this D of Z1 Z2, we can define it to be mod of Z1 minus Z2. So exactly like whatever we used to do for real numbers, we can define a metric on C in a analogous form, and exactly like you used to consider open intervals and closed intervals in case of as subsets of R. Here also we are going to have open balls and closed balls. So for example, if I have a positive radius r, then as an open ball centered at z naught with radius r is defined as set of all complex numbers z in C such that mod of z minus z naught is less than r. So this is my definition of open ball, and similarly I can define a closed ball around z naught. So this is set of all z in C such that mod of z minus z naught is less than or equal to r. So you can define it in terms of the distance or with using the absolute value. There is absolutely no difference. We will have analogous concepts of open interval, closed interval, and all that. Okay, so of course there was an ordering in case of the set of real numbers, which is going to be missing here, but nevertheless we are still going to have analogous notions of these open balls, closed balls, and things like that. And even more importantly, so you had seen that means if you, so one of the more fundamental thing in R was that we were doing all this analysis in terms of convergent sequences. For example, if you think of continuous functions, we could talk about continuous functions in terms of sequences, so or convergence of sequences, and how one function maps a convergent sequence to a convergent sequence, and like that. So those things we could do in the set of real numbers, and here also it turns out we will be able to do the same thing, and there will be absolutely no difference. Okay, and in fact what happens is that if I take a sequence of complex numbers and I can analogously define what it means to say that the sequence converges to some number. Okay, so we can define in an analogous way, and then what we will eventually see is that the sequence of complex numbers, convergence of sequence of complex numbers is equivalent to the convergence of the sequence of real part of those the sequence elements of the sequence, and convergence of the imaginary part of the elements of the sequence. Okay, so let me write it down first so we understand it better. So we can say, we say a sequence, let's say Zn in C converges to C to a point Z in C if there exists exactly same thing if there exists and not in, or sorry, so if for given any epsilon, if for given any epsilon positive, there exists in not in the set of natural numbers such that mod of Zn minus Z is less than epsilon for all n bigger than or equal to n naught, right? So this is the standard definition of the sequence convergence that you have seen in R. We can do the same thing in C also. The moment you have a distance, you can similarly define what it means to say that your sequence is convergent. Okay, so now what I wanted to say is that this convergence of sequence of complex numbers can be, this problem of convergence can be brought down to convergence of real sequences actually. Okay, so how do we see that? We see this using the following inequality. So note that, tell me if you all agree to this or not. Note that absolute value of real part of Z and the absolute value of the imaginary part of Z, both these two are less than or equal to mod of Z. Just hold on for a second, there are so many people outside. Okay, so here I'm going to, as I said, I'm going to uh, discuss the convergence of sequences of complex numbers in terms of convergence of exactly real sequences. So how do I see this? I see that the real part and the imaginary part in absolute value is going to be less than or equal to absolute value of mod z, and can also have an upper bound which is mod of real part of z plus mod of imaginary part of z. Okay, so this is what I can say. So do you all agree with me regarding these inequalities?
Yes, sir.
Yeah, so for
Yes.
example you can write down if z is a plus ib, so your real part of z is equal to a, your imaginary part of z is going to be equal to b. So this is obvious that mod of a and mod of b is less than or equal to square root of a square plus b square, and which is less than or equal to mod a plus mod b. Okay, so that's obvious over here. Okay, so once I have this inequality, tell me this particular inequality, tell me, will you agree to this statement or not, that this shows z of a sequence zn converges to z if as n tends to infinity, if and only if real part of zn converges to real part of z and imaginary part of Zn converges to imaginary part of Z as n tends to infinity. Do you agree to this?
Yes, sir.
Yeah. So what we see is that as far as the topology of C is concerned, or like this convergence and all that is concerned, there is absolutely no difference. It's just the product topology on R2 coming from R. So whatever the notion of convergence or like continuity and all this those things we had in case of R, if we try to extend it on R2 component wise, the topology that we will get, the topology on C is nothing but the same, that one only. Okay, so as far as the topology is concerned, there is absolutely no difference between C and R2. Okay, so in R2 you can define, you will see when you study a little bit more topology, you will see you will be able to define topology on R2 by taking topology from R in terms of product topology. Okay, so you say that your open sets can be written as union of product of two open intervals. Okay, so those are the things that you are going to call as open sets, and you will see that if you just think of like in Euclidean metric, if you think of open balls in R2 and the kind of topology you can get using these kind of open balls in R2 by using Euclidean distance, that is going to be identical with the topology coming from the product topology on R. Okay, so when you have topology on R, you can give a topology on R2 by taking product topology. You will study all this in topology, and like which essentially, as I said, it's what it means to say that you can give the same topology point wise on every coordinate. Okay, so therefore, as far as the topology is concerned, there is not going to be any difference. Okay, and in fact, not only this, in fact, using the same trick, what you can see that continuous functions also, there is not going to be much of a difference. Okay, so for example, if I take a function, let's say if I have, let D be a subset of C and f from D to C be a function. Okay, so we can, since it is getting mapped to C, we can split f into two parts, namely I can write it as f equal to u plus iv, where u and v are functions from D to R. Okay, so these are functions from D to R, and u is called the real part of f, v is called the imaginary part of f. So the using this equivalence of convergence of sequences, what you can say is that then f is continuous on u if and only if u and v are continuous on, sorry, continuous, what am I writing, continuous on D if and only if u and v are continuous on D. Okay, so using this sequential criteria, what you will get is that the continuity is like if I have to talk about a function defined on D taking values at C, this is going to be continuous if and only if the real part is continuous, the imaginary part is continuous. And now these real part and imaginary part are nothing but, you can treat them as functions on R, means like subset of R2 taking values in R. Okay, so therefore, as I said, as far as the continuous functions are concerned, there will not be anything which is extraordinary uh, in the set of complex numbers. Okay, so it's going to be quite the same. Okay, so there will absolutely be no difference here. Now, I so therefore the main important thing I had already told you in the last class that we are going to discuss will be the differentiable functions. Okay, I will explain why they are different and all that. But if you remember, when you were working with working on the real numbers, while defining differentiability, you used to work with, let's say, intervals of the form a comma b and things like that. So here also I need to work with something, some analog of that. Okay, now in the real line, the open intervals are like, these are simple things. And even if you think of any, there is a notion called connected sets. So the connected sets are on the set of real numbers are going to be only intervals. So therefore there is nothing much like you don't really see differences in the set of real numbers. But when you come to R2 or on C, you need to take special kind of open sets. So those are the things which I'm going to discuss little bit now before going to the differentiable functions. Okay, so I'm going to consider, since the topology is almost the same, like the topology is the same of C and R2, so we understand what are the open sets. But in our analysis, like exactly as I said, we are going to, if you just think of when we define differentiability on R, we had taken open intervals and we had worked on that. Now, open intervals had this intrinsic property that they were connected. Okay, so I will define what it means to say connected. And that is the reason why we will also enforce this particular extra condition of being connected on our open sets, and we will try to see that. Okay, so as I said, so in our analysis, we will consider open and connected subsets of C, subsets of C, and we call them domains. So whenever I say that let D be a domain, so by domain I will always mean a open or connected set. Many books write it as region. So, okay, doesn't matter. One of the name you stick to it. I prefer domain. We are going to start with open and connected sets. So for those of you who know what is connected, that's good. But if you do not know what is connected, so let me just briefly tell you what is a connected set. Okay, so what is connected? Definition of a connected set. So let X be a topological space. I'm sure you must have seen the definition of topological space by now, right? Have you seen or not?
Yes, sir.
Yes, sir.
Yes, sir.
You have seen the definition, right? Fine. So X is a topological space. We say S subset of X is connected if S cannot be written as disjoint, or disjoint written as union of, or rather disjoint union of two non-empty. So cannot is important. Two non-empty open subsets of not X but of S. Okay, so I am going to say that one subset of a topological space is connected if I cannot write it as union of two non-empty disjoint open subset of that particular set. Okay, so these are the sets which are called connected. So I cannot, so the moment I try to write S as union of two open sets, they will always intersect. Okay, so the moment we try to write the S as union of two open sets, open in that subspace topology, so open in S, so whenever I try to write it in that way, I will always get that my set is going to be like those two open sets are going to intersect. Okay, so this is called this is the definition of my set being connected. Okay, so for example, if I have to give some example, so example is for example, open interval 0 1, this is connected in R. Okay, so you can, if you wish, you can try drawing the picture. So let's say this is 0, this is 1. Now no matter what open interval you can think of, 0 to a, let's say, and then b to 1. Now if you want to write 0 1 as 0 a union b1, then you must have you must have b less than a. Okay, you will have to have b less than a, because if b is bigger than or equal to a, then you will miss some point. Okay, so this is not really a proof that 0 1 is connected, but I'm just trying to tell you like how you can imagine the situation. So this one, since you have b less than a, so therefore these two open sets must intersect, so your b should be somewhere here, so not this one. So your b should be somewhere here, and so therefore it will always intersect. So this is what it means to say a subset of a topological space is connected. Okay, so similarly, B01, this one is connected subsets of C. This is a connected subset of C. So I'm not going to prove all this. These things you will anyway see it in topology class, but you can take it for granted at this moment. Okay, so in fact, you can also prove that connected subsets of R are intervals. Okay, so if I take any connected subset of R, it has to be intervals. Okay, so it could be unbounded interval, bounded interval, I don't care, but any connected subset of R has to be an interval. So you can prove that. But of course, that does not mean that in C the connected subsets has to be only open balls. In C you can have various types of connected subsets. So for example, if I try to draw this kind of, if I take a half plane, that's going to be connected and things like this. Okay, so I can have various types of connected sets in C. In R, of course, our choices are limited. Okay, so one subset I can give you an example which is not connected in R is this one. Okay, so this one is not connected in R. Okay, so for example, you can see that this is a union of this one and this one. Each of them, a priori, they are not open in R, that's true, but they are nevertheless open in S. So in the subspace topology, these two are open sets in the subspace topology. So therefore, if I take this set is not connected in R. Okay, so you can have, like, you can keep these examples in your mind. So there are several kind of connected sets that you get in the set of complex numbers, but in R you only get the intervals as connected sets. Okay, so now these intervals, if you just look at in the set of R, in the set of real lines, real numbers, and if you just look at the intervals, then you have, for example, you can imagine that if I have 2 points in the interval, so if I means by definition in an interval, if you take 2 points, all the points in between those 2 points, they are going to be there in the interval, right? Now of course in C there is no ordering which works well with the topology, so we don't have this concept of interval in C anymore. But what we can talk about is that we can talk about like we can imagine, try to imagine the situation in the interval as saying, I'm trying to say that all points between A and B are there. You can try to imagine it by saying that the line joining A and B is in the interval. Okay, so in R you have this nice feature that since only the connected sets are only the intervals, so if you take 2 points from the interval, of course you know all the points in between those 2 points are in the interval, and you can reinterpret this in the following way, that if you take 2 points from the interval, then the line joining between those 2 points are also in the interval or in the set that you have taken. Okay, so This is something which is a special property which is called the property of path connectedness. And again, this particular property of path connectedness is something which is not explicitly visible in the set of real numbers, because as I said, in the set of real numbers, every connected set is of the form of an interval, and in interval this notion of path connectedness is just vacuous. Okay, so you really do not have a this notion of path connectedness is really nothing different in the set of real numbers. So in the set of real numbers, the connected sets are intervals, and those are the path connected sets. So this concept of path connectedness, which again you will come across in topology course, so it's a stronger stronger condition than being connected. And this particular thing, the difference of these two, you do not in general see it in the set of real numbers. Okay, so of course there is a difference between the notion of connectedness and path connectedness, but for the example you will have to go to at least on R2. Okay, so on R you do not see any difference between connected and path connected sets. So let me just give you the definition of path connected set so that you have this in your mind. So I was telling you what happens in case of an interval. In case of an interval, if I take 2 points, so then any 2 point joining between those 2 points are there. In other words, the line joining A and B are there. Okay. Now the line joining A and B, you have seen the formula. There is a way to express given equation of line joining A and B, and it turns out that equation is just a linear function, so that's going to be there. So what we are, and a linear function is a continuous map. So in case of path connectedness, what we say is the following. We say that a subset S of a topological space X is said to be path connected if for any 2 points A comma B in S, there exists a path from A to B lying in S. Okay, so in that case I will say that my set is path connected. Okay, of course now you will ask me what is the meaning of a path. I will tell you what is the meaning of a path, but first let us try to understand the definition of path connectedness. So path connectedness means you have a path, like you have a set, and no matter which 2 points you take, you will always have a path to go from one point to another point. So what is a path? And by definition, a path from A to B is a continuous map f from closed interval 0 1 to S, such that f of 0 is equal to A and f of B is equal to 1. Okay, so this path lies in S. That means the function, it should be a continuous function starting from an interval 0 1. So in place of 0 1 you can have anything 0 2 0 5 or 5 7, doesn't matter. A function, continuous function from a closed and bounded interval to S, such that the first end point of the interval goes to A, and the last end right end point of the interval goes to B. Sorry, I wrote it wrong. F of 1 is equal to B. So this is what, if you have, then that's called a path. And to say that a subset S of X is path connected means that you will always have a path, that's a continuous map, going from closed interval 0 1 to S, going from one point to another. So for example, if I try to draw some picture over here, So this one is path connected. So for example, if I have A and B over here, you know, here in fact the straight line joining A and B is coming out, is staying here. But let's say I have a complicated picture, something like this, and I take A and B over here. So I don't have the straight line joining A and B, but nevertheless I can still figure out a path like this going from A and B, which is lying entirely inside my set. Okay, so if I have this kind of a phenomena, then we will call our sets to be path connected. Okay, so this is an additional notion, and of course this is, I am not going to prove, but it's an exercise, or later when you study it in topology you can see, or you can try to prove now itself that path connected sets are connected. Sets are connected. Okay, so try proving that path connected sets are connected, and therefore means this is something which is a stronger notion of connectedness. So you will see example again in topology book, or if you just google it. So there are connected sets which are not path connected. Okay, and you will get example in R2 itself that there are connected sets which are not path connected. Okay, so I am not going to give you that example, you will see it in topology course. But what is important in our case is the following one. So in our case we are going to have this important property, that, so I told you already that I am going to work with open and connected sets. So I'm going to work with open sets as well as connected sets. So what it turns out that in C, so domains, that is open and connected sets of C are path connected. Okay, so what I'm saying here is that if I start with an open and connected set, then it's going to be path connected. So as far as the open sets are concerned, there is no difference between connectedness and path connectedness. Okay, so if you are looking for an example of a connected set which is not path connected, you must not take an open set, because if you take an open set it's not going to work out. Okay, so what we have over here is that an open and connected set is going to be path connected. So this is one which is very important property that we are going to use very much in our analysis, especially when we study differentiation. So I'm going to give a proof of this now. The more important thing that we are going to do, you see, when uh, we were doing differentiation on R, we were having intervals. Now when we had intervals, we could use various theorems, for example mean value theorem and various other kind of things which were typical of intervals. Okay, and now if I have some arbitrary set which is even means whether it is open or not, I will not, like let's say in R2, I don't have this kind of luxury because I don't see every set as an interval. Okay, so that is the reason why this particular theorem is very crucial for us. That this particular theorem, in fact I am going to prove a stronger version of this particular theorem. So this particular theorem is going to actually enable us that we will be able to apply some kind of mean value theorem wherever required. Okay, so we will have to do some adjustment. We don't have in general line joining A and B or an interval, like we cannot means really have this concept of interval, but nevertheless we will be able to use a similar kind of trick for our purpose. And the main important point that we are going to use for this is that domains in C are path connected, or even something more. So I'm going to write this path connected, moreover let me write, they are polygonally connected, polygonally connected. Okay, so they are going to be polygonally connected. So that means what, I can have, so here you see, from in this picture, in the first, in the picture on the left, I had the points A and B, and I went from A to B by one some continuous path. But what this polygonally connected means, I can go by means of straight lines. Okay, so I can go from A to B by means of straight lines. Okay, it might not be one single straight line, but nevertheless I can make multiple small straight lines, and I can go from A to B by means of straight lines. Okay, so this is what it means to say polygonally connected. So polygonally connected means the path that we will have, that path is going to be a polygonal path. So it's going to be, so every means like we will always have segments of that path to be like, if you look at, means you will have points on that path, so that uh, the actual path can be seen as line joining those points, okay, consecutively. So those are called polygonal path. So in fact you are going to have that domains are polygonally connected, and even something much more than that. So I can even have something better. I don't even need polygonal paths. What I am going to have is that I'm going to always, I will always be able to find paths which are either going on the horizontal direction or on the vertical direction. Okay. So I can take polygonal paths which are where the line segments are always either vertical or horizontal. Okay, so this is how you can connect any 2 points A and B in an open and connected set. Okay, so if you have an open and connected set, it's going to be path connected. More than that, it's going to be polygonally connected, and even more than that, it's going to, so that polygons we can choose in such a way that the line segments of the polygon are going to be like, or the line segments of that path are going to be either vertical or horizontal. Okay, while we are going to stay inside the domain itself. Okay, so is this clear what I have said so far?
Yes,
Yes, sir.
Yes, sir.
I have said
Yes, sir. Yes, sir.
I have said many things, but I hope I could convey some of the important points. Okay, certain features you are going to see it in topology course. Hence, I don't want to say too many things about that. But what is important for us, I am going to say that. So the important part for me is to have this polygonal, like that the domains in C are going to be path connected. Okay, and more precisely, they are going to be polygonally connected, and even more precisely, I am going to find paths from A to B where the paths are made of line segments, where the line segments are either on the vertical direction or on the horizontal direction. That's all. So I am going to move either on like to my left or right in the vertical, in the horizontal direction, or to my means I am going to move up or down in the vertical direction. I'm only going to do it in this way, and by doing that, I'm going to reach from A to B, no matter what point A and B you take on an open and connected set. That is what I want you to take. And once we have this understanding in place, you will see, as I said, I will be able to apply one variable, some basic mean value theorem and things like that, which will be useful for our purpose. And that is why I am doing this, because you see, once I have these kind of straight lines between 2 points A and B, whether it's vertical or horizontal, so I can say that I have increment in only in one direction. So therefore means like increment in only in one coordinate. So we will be able to take some partial derivative and things like that, and where we can apply some mean value theorem and those kind of tricks. Okay, so that is why it is important for me to have this stronger notion of connectedness, not only connectedness, but these kind of polygonal connectedness where these line segments are going to be either horizontal or uh, vertical. Okay, so let me give you a proof. I'm going to prove it only for the path connected part, and you will be able to suitably modify this to show this polygonal connected or this vertical, horizontal, and all that. Okay, so it's just that I have to write too many notational things, hence I don't want to do that. So let me prove the path connected part, and I will leave it as an exercise where you will prove that it's you are going to get horizontal and vertical line segment and all this. Okay, so let let what happens, yeah, so let D subset C be a non-empty, open, and connected subset. So I have to show that A and B are like, so D is path connected. Okay, fine. So fix a point Z not in D. Okay, so and then we define two sets. Define A is those points Z in D such that there is a path from Z to Z naught. Okay, and B is that set Z belongs to D such that there is no path from Z to Z naught. Okay, so I am saying this thing. Okay, so clearly D is equal to A union B and A intersection B is empty. Right? Agreed? This is just from the construction itself. Correct? Yes or no?
Yes.
Do you agree to this?
Yes, sir. Yes,
That
sir.
if I define my A and B
Yes,
like
sir.
I have this one. Okay, so now can you tell me that if I show that D is equal to A or B is equal to empty, will I be done? For example, if I show that D is equal to A, will I be done?
Yes.
Yes, sir.
How?
Sir, sir, if we show कि B is empty, then it is enough.
Yeah, if you are saying this is enough, yeah, that's true. But I am asking, suppose I show D is equal to A, how does that complete my proof?
Then there is a part between Z and Z naught. But Z is and Z can be any point. Z naught can be any point from the.
Yes, no, Z naught is fixed. Z naught I have fixed, and I have defined A and B like this. And I am asking that suppose I am able to prove that D is equal to A, then will you agree that I am done? So if you agree, tell me how do you agree?
Then there any part can be built by such many parts.
Sorry, I did not follow you.
Sir, if D equals to A, then B it becomes empty.
Yeah, P becomes empty. That's fine. But I'm saying my proof will be done. How? My proof is done.
Then when we pick up need 2 points, then there's those 2 points can be separately joined to the Z naught.
Absolutely, and therefore I
There
can,
is part.
and then I can connect. Then I can say that okay, I can join these two paths together, and I will get a path from A to B. Absolutely, that is what I wanted to hear. So if I can show that D is equal to A or B is equal to empty, we are through, right? Fine, agreed.
Yes, sir.
Yeah. So now to show that D is equal to A or B is equal to empty. So what we are going to show first is that both these A and B, these two sets are open sets. Okay. That is what we are going to show first. Number one, that we will show that A and B both are open. Okay. And now we have what? We have that D is a connected set. Okay. We are going to show that A and B. So we show A, B are open. And now I know what? I know D is connected. And connected means what? I cannot write it as disjoint union of non-empty open sets. Right? That is what the definition was. that I cannot write it as disjoint union of two non-empty open subsets. But if I can show that A and B are open, and I see that D is equal to A union V, then I must be having at least one of them to be empty. Correct?
Yes, sir.
Yes. Now, why A is non-empty? Because already I can find a path from Z0 to itself. So, for example, Z0 belongs to A, right? So, therefore, A is non-empty, and that will imply B must be empty, and hence A will be equal to D. Okay, so let us quickly see why A and B are open. So, the proof is very simple. So, we show and clearly, so clearly this I should write A is not equal to phi, as Z not belongs to A. So we will show that A and B are open, and hence as D is connected, we must have D equal to empty, and this implies D equal to A, which implies D is path connected. Okay, so this part we have already discussed. Let us now quickly show that A and B are actually open sets. Now, to show some sets are open set, what do I have to do? I have to take any point and I have to show that there exists an open ball around that set, which is contained in my set A or B, whatever you want to take. So the proof is not at all difficult. How do I do that? So let Z belongs to A. By definition, D is open. Okay, so there exists delta positive such that BZ delta is subset of D. Okay, so BZ delta is subset of D. Now my claim is that this BZ delta is actually subset of A. Okay, why this said BZ delta is subset of A? Can you tell me quickly why this BZ delta is going to be subset of A?
Sir,
So I
A is
that
open. A is open
that belongs to A.
because A is open.
No, because not because A is open. I want to show A is open. So I need to prove this one. Now this is the proof of that A is open. We show this. Okay, so this is the proof that A is open. That is going on. So I have to show that this one is subset of A. Okay, so to show.
That is connected.
Sorry. So well, tell me.
Open sets are connected.
No, here still I don't have anything to be connected. So let us see. So first of all, observe Z belongs to A implies there is a path from Z to Z naught. This is by definition, correct? Now let some Z prime belongs to BZ delta. Now just try to imagine what is BZ delta, just some ball. Okay, it is just some ball centered at Z. Okay, and Z prime is somewhere here. Now always there is a path from Z prime to Z, namely the straight line joining these two, which will lie inside BZ delta. Correct? Yes or no? If I take any ball,
Yes, sir.
it's very natural. You take no matter what point you take in that ball, you will always be able to connect it with Z. Right? Just by taking the line joining those two, it's going to strictly stay inside this ball. So now let this is this, then the line joining Z and Z prime lies in BZ delta, so which lies in therefore D. Okay, so line joining Z and Z prime lies in D. Now, so therefore I understand that there is a path going from Z prime to Z, and we already know that there is a path going from Z to Z naught. So Z naught is somewhere here, let's say, and there is a path going from Z to Z naught, and already Z prime to Z, we see that the line segment is there which joins Z and Z naught, and the line segment strictly lies inside D. Okay, so therefore there is, so here all these things, there is a path means path in D, huh? So all these are path in D, that is important. So therefore there is a path in D, everything is in D, so there is a path in D from Z prime to Z naught, hence Z prime belongs to A, that is BZ delta is subset of A. Okay, is this clear to all of you?
Yes, sir.
Yes, sir.
So therefore what I see, so this implies, let me quickly say, the time is running out, A is open. Okay, so now I leave it as an exercise for you to show that B is open. So do it as an exercise, because there is nothing to again the proof is going to be exactly the same, because you take any point from B, you consider an open ball which is completely inside D, you will be able to say that that particular open ball is in B, because if any of the point in that open set is connected to Z naught by means of a path, then the center will also be connected to Z naught by means of a path in D. Okay, so therefore you will be able to say that B is also open, you will be able to show, and once A and B are open, just use connectedness to say that A is equal to D, and A equal to D implies D is path connected. Fine, so please complete this proof. There is nothing difficult over here, and exactly the proof is going to use exactly the same idea, that you will be able to have a ball, and once you are able to have a ball, you will be able to, whether if your center is connected to Z naught, all other points are going to be connected to Z naught, and if your center is not connected to Z naught by means of a path, no other point of that ball can be connected to Z naught, because otherwise then if any of the point of the ball is connected to Z naught by means of taking this uh, line joining, you will get a path from Z to Z naught. Okay, so in that way proceed and complete this proof, so you will get that every open connected set is path connected. And now to prove this additional thing, this polygonally connected and all the extra bit which I said, that you can have a polygonal path which is either on the vertical direction and or on the horizontal direction, you can just replace here. So I said there is a path, so you can replace the word path by polygonal path, or path by polygonal path which is either horizon having line segments, horizontal having horizontal and vertical line segments and all this. So you can replace it with these things, and in the open ball you can see that if I have any point in the open ball, I can always connect it to the center by means of vertical and horizontal paths. So if you notice that, then you will be able to say that in place of path, if you replace it by polygonal path or by this
Actually, sir,
yes,
so we have next class,
yeah,
right?
so yeah, I'll just stop here. So yeah, please try to fill up these details, and